This is the entirety of the Earth's atmosphere, consolidated to showing all layers, including the tropopause, the mesopause, stratopause, the mesopause, so on and so forth. This explains the temperature differences between each of those points. This here represents the entirety of the Earth's magnetosphere and the various bands within it. The blue within the plasmasphere right here represents all of the entirety of Earth's atmosphere. Earth's atmosphere stops at the end of the blue and is only confined and contained through the magnetosphere. Where are we in space right now? Here. This is 230 miles up. 230 miles is because this is the safe orbital place for us to not be fully ionized, but still have the the ability to stay above an area in which we have found consistently it falls down and receives heavier extreme X-rays. We started in space travel in 1957, achieving this point right here. Human beings exist within the green bands of this area. You start to need oxygen as you get to the top of, say, Mount Everest, and when you're flying up in planes here, you need cabin pressure in your own atmosphere. Weather balloons, various NOAA and NASA weather satellites and balloons, or not satellites, balloons that fly up high are up in this area, and higher above that is our greatest military airplanes. Neil Armstrong took the rocket plane that they invented, VX, whatever, and touched the mesosphere. That was about the scariest ride of his life, and that's the peak of our ability to fly, because as soon as you get to this point right here, molecular structure starts to break down, and you come into microgravity. There is no longer the ability to have planes or any of our various things. So from the 40s and the wars, we shot rockets, but we shot everything within this field. In the 50s, we moved up to here. That's when we started shooting satellites like Sputnik and stuff, and we started hitting low Earth orbit in '61 with Alan Shepard, and Yuri went up here and died a few years later of radiation exposure because he went a little bit too high in his pattern before he was able to come back down. And they also killed a few other people, but there's nothing in the history books about that, so it's just hearsay. So we met up after we sent the Mercury, Gemini, Apollo missions up to about the 230 mile mark when they were up there in the Soyuz, flying around this area right here. It's the most stable for orbital patterns. It can be habitable, as well as any radiation exposure can be dealt with transitional metals, basic things like water shielding or titanium. Shield because of the various layers of atmosphere and shielding from the magnetosphere well above it and surrounding it. So it only gets the last little bit of ionization from E and D bands. It's not really getting any of the F1 or F2, so it doesn't get extreme ultraviolet radiation bands like you would in any of the upper heliophysics satellites where they're studying things. So when we hit that point in about 1975, and we all hit this cap. Apollo's Soyuz rendezvoused in 1975, and from that point on, it was kind of a political nightmare for a couple of years. But in the 80s, they ended up making space shuttles, but then Russia went with the Soyuz because it was more appropriate for their missions. Their missions being, have and maintaining space. As well as planting stuff up there, so they thought it would be best to just continue with what they were doing. They built the shuttle. We built the shuttle to start bringing things up into this area of space right here, lower and mid-thermosphere, to study space with things like the Hubble and various endeavors with planting communication satellites and things like that. In 1997, we had found out that the Mir had been floating around for a long time up here, and where it was starting to come to orbital decay. The Mir MIR was a Russian spacecraft that they built a long time previous before by themselves. As we tried to build Skylab and it failed, we gave up just as the shuttle decided it'd be easier to just fly up and come back down. They still stuck with the original ways and launched stuff up, put it back together up here, and then stayed up in it. So they had their space stations long before the International Space Station. And during that time, they had figured out, the best orbital positioning, so not to fall to orbital decay and so on and so forth. So they had been up there. In '97, we finally came and had some decent agreements politically, and finally allowed them and us to all participate globally again. And in about 1999, we set up on the International Space Station, and they sent with their Proton rocket, they sent the first piece up. It made it 230 miles up. We assisted with a bunch of our shuttle missions, pieced it all together. By 2001, we had a fully habitable International Space Station, and science fully started trying to figure out exactly what to do when we are up here and how our bodies react and everything that reacts when we take it up there and why. So for a few years, we started figuring out why right here and on up is so dangerous to us, and all things like this that is formed in the atmosphere layers down here. So in 2001, one of the most important missions NASA has ever sent, Genesis, was launched up to about the 3,800 mile mark here. It didn't work out for them. It failed because of the ionization that occurs up in the upper exosphere, because of the ionization from the ionosphere not being fully filtered like it is for us in the lower layers. And it ended up fritzing, and so the probe that was supposed to gather the raw energetic particles from out here that we can't be exposed to and we can't fully touch, it ended up crashing back to Earth, and everything was exposed, and unfortunately the mission was scrapped. So they had to try again later, but what they did in the meantime was they shot up a ton of heliophysics satellites. I could go off, there's 40, 50 per country, and they're amazing. I suggest you look into all of them, just nasa.gov. So if you take into consideration Orion being one of the missions that's upcoming, you'll note that it is actually, it has been a previous mission before, but it's not very even though it's going to be the future mission, it was previous one and failed. It's not very widely discussed because of its failure. However, it was also launched in 2014 to go where Genesis failed, and they wanted to go a little bit higher than where we had done the manned flights at about between 500 and 1,000 miles. I mean, they were dangerous as it is. So we sent Orion to the 3,800 mile mark to see whether or not any of the systems in that capsule would fail, such as various other ones have when exposed to the heavy ionization. And unfortunately, it played out the same as Genesis and the various other ones that have been sent up that high, and it ended up shorting out. It came to rebooted when it was able to. It shot back with its emergency protocols, and they're very clear about, in the video they present later, they show the capsule failing because of the ionization, and they need to figure out exactly how to create active shielding that's strong enough to be what we have down here, to be up here with it, and so on and so forth, the greater as you go out. So they pulled back, closed everything up a little bit, and they pushed out all of the other things. They allowed SpaceX and Blue Origins and all the various companies to come in and participate in trying to not only duplicate the capsule, but participate in shielding and ideas on how to do velocity escapes, various things like that. When they finally figured out that they're going to need to be able to study the particle before they can make the actual shielding for it, such as, you can't tell me that an electron turns without putting it in a vacuum chamber first, so you need to have the actual studies completed before you can understand the science to make something counteract the science. So we, on Earth, decided GSI needed to show us through their proton accelerators how exactly these cells interact with the human tissue, because we don't want to send something up there and kill it, and we know now what happens with electronics. So now we need to figure out what happens with the human cell, as well as what will happen to the neurology of the human mind, being that it is also an electronic computer system. It runs off the same juice. So, well, after they presented their study, they showed very clearly that the alpha carbon particle that they created that is similar to the solar wind, they were suggested would be up here by NASA's projected simulated data. they showed that it would completely annihilate the nucleus and no usable RNA would come from it, thus it would be a cancerous cell or just decay in itself. And the human being, depending on how many particles it interacts with, and being that there is at least one particle per particle of yours out there, it's a C. This is far less than being out here, and I'll explain that in just a moment. But they suggested that if you wanted to leave out here, then you were going to need to encase the entirety of a magnetosphere around the craft that you're trying to leave the magnetosphere with. So not only you would have to have all of your atmosphere and the basic shielding that it requires, but you would need to have an active shielding around it to ensure that it can continue outside of the active shielding that the Earth has provided. And so NASA came back and went, okay, well, now we need to figure out exactly how to shield it. And they said, well, are you certain about the particle? And he says, well, I mean, I made the particle through your suggested data, so this is the best we can do until you actually touch it. So they decided then to make the Parker Space Probe. The Parker Space Probe is not actually going... They say it's going to the sun's atmosphere, and that's exactly what it's going to do. It is going to touch the sun's atmosphere. However, the sun's atmosphere, as we know it, is the end of the exosphere. The end of the exosphere, being 6,213 miles out, is the end of the blue right here, which is in the plasmasphere. Plasmasphere is exactly what we're trying to touch. Raw particles from magnetic reconnections throughout the neutral point in the plasma sheath, as well as all the points in the magnetosheath and the various polar cusp points that allow it to come in to radiate down to make the aurora borealis. They want to touch just that right there. And so that is literally just touching the edge of this exosphere right here. That is the sun's atmosphere. So they launched out Parker Probe to go around and around, just like Genesis did. It'll take a while for it to float, just like the Hubble takes a long time to float up, Spitzer takes a long time to float up, Kepler a long time to float up. Eventually, when they hit the end of this, we flip them around, like we did Voyager 1 and 2, take a picture of the Earth, the best cameras we got at the time. Kepler's was just fucking amazing. I love, because Earth is black and white, everything's black and white, everything's so bright out there. It was an amazing picture from out there. And so, we eventually will sling it around as it's floating up, and it will, through gravitational sling, through Earth's orbital patterns, it will push itself out, and it will finally take a sample. And we will hopefully, at that point, third time's a charm, we'll be able to understand and get a raw particle from that. And then we'll be able to move on with trying to figure out how all this works. Because right now, as far as we can go, is 230 miles. The end of the atmosphere is 6,213 miles out. That is just the end of the blue right there. Now, if you were to shoot through this, as they say, we could go out really fast this way, that's impossible. That's shooting a bullet into a sea of lava, a paper bullet into a sea of lava with what we have. And then not only is it going into the heaviest, absolutely the thickest layers to leave, or if it goes out this way, it's going into a shotgun of all of the exiling, released particles from all of the magnetosphere's tail. So there's no way out through speed. Plus, when we get out here, we have found that this is 100% of what is surrounding the Earth's active shielding. 1% makes it into right here. And this is what interacts with the magnetic reconnective points in itself, causing this plasma state. And then through the magnetopause and through the polar cusps, a few make it down, most of it leave through the tail, but through the neutral point it finds its way back through. All of these find its way into, just at the north and south points, they find that 1% makes 1% into us, and that 1% of that 1% is filtered all the way down, and there is where the last of it finally is filtered out through the ionosphere, and it stops, and we get those beautiful aurora borealis lights, and everyone oohs and ahs at the greens and purples and the beauty of it all. However, we are barely shielded by it. Climate change has everything to do with this, the consolidation or the deatomization of various layers, as well as the weakening of certain bands. So, yes, we cause climate change with our carbon buildup in our areas, and this will kill us long before the Earth dies. This will resettle. We'll die, though, from what we've done. It will not help that the heavy ionization will cause us to die because of the carbon amounts we put up there. So we're heading towards destabilization of our atmosphere because of loss of O3 and the various elements that they talk about very clearly on nasa.gov, leaving our magnetosphere. That's why the seas aren't rising, as we are losing the elements just as fast as they're being ionized. They do go away. Notice why balloons cost more. Helium is in great depletion. So, we can't just go up and out, or you're going into 100% of that 1% that we get 1% of. So within that 1%, of that 1%, into that 100% is certain doom. That's why we have to stay safely here within the layers of atmosphere that are still filtering us, within all the passive shielding we can take up there, very, very safely within all of Earth's active shielding. The moon is the size of the tip of my pen, and it is 230,000 miles out. 230, now remember, 620, this is 25,000 kilometers, 25,000 miles out. So if the moon was, say, back here, and we could go all that distance, it would be here. This is where the moon would be. This is why we can't leave Earth, and this is why they don't worry about climate change.